Hello, my name is John. Today I'm going to be presenting to you guys this combined spectral problem using the chemical formula C10H12O. So we're going to be walking through this combined spectral problem and determining the structures of an unknown compound with the given molecular formula. So the first step is to calculate the degree of unsaturation that's down here. That's this du. That'll give us some clues about the rings and the bonds in the molecule. Using this formula, it will be 2C plus 2 minus H divided by 2. So to calculate that, we have 10 plus 1 minus 12 over 2, and then minus 6, so we got 5. That's 5 total degrees of unsaturation. And that's quite a decent number. It's suggesting that there's a combination of rings and double bonds, possibly including a benzene ring, which accounts for 4 degrees total alone. Next, we did some IR spectrum analysis because there's several key peaks. There's a broad range of 3,000 to 2,850 centimeters. Minus 1, and that's indicating CH stretching from both aliphatic and aromatic sources. There's a strong peak at 1,700 centimeters, and that confirms that there's a presence of a carbonyl group. That's a double bond with or a carbon to an oxygen. There's peaks at 1,500 to 1,600, signaling double bond carbon stretching in an aromatic ring, and then there's a peak around 750 to 700 supporting that there's another aromatic carbon hydrogen bending. The data that we got here suggests that we're looking at aromatic ketone, probably something like our carbonyl group or an aryl group. And then going to the 13C NMR spectrum analysis, we see I have 7 total different carbon environments. There's a peak at 1900 ppm, showing that there's a carbonyl carbon consistent with a ketone. There's peaks at 125, 130, 135, and 155 ppm, which are characteristic of aromatic carbons. The one at 155 ppm is slightly deshielded. This might be due to its position next to the electron withdrawing group. And we see peaks at 14 ppm and 35 ppm, which indicate aliphatic carbons. At 14 ppm, there's a carbon, likely a methyl group, a CH3 bond, while the 35 ppm carbon is likely due to a methylene group. It's a CH2 bond, suggesting that there's some kind of alkyl chain or branch group on the molecule. Now we're going to the 1H NMR spectrum. We start with a signal of 1 to 1.5 ppm integrating for 6 hydrogens and appearing as a doublet, suggesting that there's 2 equivalent methyl groups, each next to a CH that only has 1 proton. Next, there's a signal around the 3 to 4 ppm, suggesting a multiplet, integrating for 1 hydrogen, which is likely a CH proton bonded to 2 methyl groups, forming an isopropyl or tert-butyl-like structure. Finally, in the 7 to 8 ppm range, there are 2 separate multiplets, integrating for 3 and 2 hydrogens, respectively. This fits with a monosubstituted or unsubstituted benzene ring, giving us 5 aromatic hydrogens total. And then, so totally, going over this whole worksheet here and putting the pieces together, I'm proposing that the molecule is isobutyrphenone. Sorry if I butchered that. It's a phenyl group bonded to a carbonyl group, which is then attached to an isobutyl group. And the given structure that I outlined here accounts for the data above, the carbonyl and aromatic signals in IR and NMR, then the 7 distinct carbons signals in the 13C NMR, and the proton splitting patterns and integrations in the 1H NMR. The six hydrogen doublet and the 1 hydrogen multiplet together form a CH3 2 CH group, and the 5 aromatic protons support a monosubstituted benzene. This problem demonstrates how spectral data from multiple sources can be integrated to propose a given structure. And each piece of the evidence contributes to a clue, and then which combined they paint a full picture of the molecule's identity given here. Alright, thank you.